Perfect. So hi, everyone. Today we're going to talk about rethinking scalable machine learning with Spark ecosystem. We're going to talk about how we can leverage AI, why we need to think about massive amounts of data, why distributed machine learning is on the rise. You probably heard about different tools today or during there's this wonderful conference around Ray and other technologies, and overall, why we see such a huge demand for machine learning, productionizing machine learning, ML ops, and the different tools that exist in the industry. So I hope you're excited. I am definitely excited, and let's get started. So like we mentioned earlier, my name is Polak. I'm managing a team at Microsoft. I co-created the data engineers community. You're most welcome to join us. We talk about different challenges we see in the industry, from fully supporting the data scientists to the analytics team to how to build the data infrastructure, data ops, privacy, security, a lot of great conversations there. So you are most welcome. I'm currently writing a book for Riley about machine learning with Apache Spark, how to build the pipelines and the different tools that exist in the industry around the Apache Spark tools. I'm a Databricks beacon, and I have more than decades of hands-on experience in the machine learning and scalable data infra. So let's get started. Today, the goals for you is to understand why machine learning is slightly different than how we do code. What are the different steps that we're going to take to productionize machine learning? Why data is key when we look at small versus large data set. There's always a conversation of, do I need more of a 1 gigabyte data set to train my machine learning, or can I use just 100 small files like CSV and stuff? What Spark gives us out of the box, and how we can craft a model at scale, looking at MLlib, and how we can bridge Spark and deep learning as well. So let's start from the beginning. Machine learning is different. When we think about it, often when we write code, we deploy it to production, it runs, it takes some data, all is good. But here, actually, we need to produce the machine learning model first, right? We know we take the data, we ingest it into some algorithm. It can be algorithm from different libraries, PyTorch, TensorFlow, MLlib. There's a lot of libraries out there today. It produces a model. Then we take that model, we wrap it up, and we add more data into it, and we put it into code, and that code gives us answers, right? So we inject the code with data, and we get back answers. So it's a very high-level, simplified idea of what we do in machine learning. But how the data scientist process works. We get the data ingestion, we get data in our system, we do the cleaning, transformation, some feature engineering, domain expertise, and then we train the model, we test it, we validate it. Maybe we change a little bit of parameters there, hyperparameters, we change the algorithm that we're using, and then we're pushing it forward, right? From a data scientist perspective, we're pushing it forward to staging and deployment, and this is about the end of it for data scientists. But productionizing machine learning, it's slightly different conversation, right? Because we have to think about the different stages that we have, the different stages that we go with code before we push it into production. Any software, we do go through those stages. So we have the development stage, the staging stage, and then the production stage. And we're going to talk about each stage a little bit deeper to understand where are the challenges and what are we facing today. First thing first, development stage. And in development stage, often with data scientists and machine learning workload, we're going to look into two different stages within the development stage. So the first one is going to be when we're working on offline data. We're trying to understand what the domain problem is, what the data that is available for us, how we can train the models, which algorithms we want to use, a little bit of understanding of the feature engineering process if you want to take. And all of that, something that we do often on a small data. And this is great. However, it imposes some challenges. Code is not built for large scale of data, right? We use tools that we can work with on our local machines. And code is definitely not production ready. We work on our local machines, it's offline, small, sample data. And this is great because it allows us to try multiple algorithms, features, hyperparams, like really get into the nitty-gritty of the data and what is available for us in there, really get that domain expertise shine, really understand the domain problem as well. And this is great until the data science often call the data engineers or the rest of their team and say, hey, I just discovered that the accuracy of my model, it's not so good. I mean, it's fine. It's a good start. I know what the features that I want maybe, but I need more data. I need more XYZ data streams into our system because I need to develop more features. It's not enough, right? I need to bring in and enrich my data. My CSV strings somehow are not loading properly. Something has happened along the way with the formatting. And the biggest ask that we see all the time, that data is not diverse enough. It doesn't reflect, it doesn't help me solve the business problem that I'm trying to solve. And this brings us to the question around data, why data is so important in our machine learning workloads. And we can look at small data versus large data set, and each one of them has benefits and also brings challenges to our system as well. We know with small data set, it's a little bit hard to appraise the real worth of the representative of a particular sample. Like, it's really hard to define a set of rules to solve a specific challenge. However, from a compute perspective, it's easier for me to run it on my local computer. I don't need an extensive skills to run it on my local computer. The tools exist also. There's a lot of open source tools that exist out there, right? So I can start working right away. However, with a larger data set, I can get a better chance to encapsulate and represent the domain problem, or to solve the problem that I'm trying to solve, the problem, basically, the business problem. However, it requires a cluster, multiple machines. It requires, or a very strong machine that can be pricey. It also requires sometimes software that is proprietary, closed software, or some tools that I'm not aware of, or I don't have access to, or not part of my skill set. So after we went through the first stage and we realized kind of, okay, we understand the overall flow of how we want to build the data scientist part, now we're going into the second stage of my machine learning experiment, and that's leveraging tools that are available to operate on top of large data set. So in the second stage, I have a larger offline data. I'm still working in a batch processing manner. I have a larger offline data set, but that requires specific expertise, right? Not all of us are expert on, Apache Spark or Ray or all those great distributed systems, tools, frameworks, and that requires a certain set of skills. It also requires to have a running distributed environment, which we don't often have access to. However, if we work with the different clouds, we can easily get one running for a certain price. So after we went through the first stages of development, and let's assume we're happy with the result, we kind of understand that we need to learn a little bit of new tools and leverage some tools that exist in the system, maybe work with the data engineers to get it into from the first stage to the second stage of development. Then we want to push it into the staging, right? We got a model, we're happy with the model, and now we want to test it again, test the integration around it, wrap it in code, and try it, and maybe even try to build that model again on a fresh data if we need to, or estimate the accuracy and the quality of our model in staging. So in this phase, we're actually translating the code to a production environment. And we're testing it again and again and again to understand if it stands with the standards that we expect it to stand in when we push it to production. So this is the staging phase. After we're happy with it, we get, go, no go. If we decide to go with it, we push it to production. And inside production, we still have a similar process of data ingestion transformation. However, now with the thing that we're pushing the model, right? We're not pushing the training phase. We're pushing the model, and in production, we're using the model to either score, predict, analyze, or do anything, capture, or do anything related that get an answer about the user, what they're going to do. And then we also need to capture the user real action, right? Because we need to compare those two results from what the model gave me as a prediction and also what actually happened in reality, so we can monitor it and give and refresh the model when we need to. So we use the model for scoring, we capture user real action, we sync the data for monitoring, and then we always ask ourselves, do we need to trigger a new ML workflow? Is there a data drift? Is there a model drift? Do I need to change something? So this are kind of like the high-level stages that we see in productionizing machine learning. And now that we understand it better, let's understand what specifically Apache Spark gives us. First thing first, it gives us the ability to work with data. It allows us to ingest data from different sources. It allows us to run cleaning, transformation, feature engineering, and all of that leveraging the very rich capabilities that Spark has out of the box. And if you're not familiar with Apache Spark, it's a unified analytics engine for big data and machine learning. It was originally developed in UC Berkeley in 2009. And since then, it was the go-to tool for big data analytics and anything related to distributed computation. So like I mentioned, it has a rich API. You can use SQL-like capabilities. You can use structured streaming, different capabilities on top of data frames. It also has ML library, which is the one we're going to touch deeper into today. So we say we're still in the first phase. We need to run the featureization, the feature engineering. So in Spark MLlib, it gives us the ability to extract and transform features because there's a lot of capabilities already out of the box. It also gives us utilities because in machine learning, we work with statistics, right? We work with math. So it gives us linear algebra and statistics and kind of gives us tools, like summary tools to get a feel of what's going on in the data. So this is great. We cover the data. Now we need to craft the model, right? So we are in the second step, in the third and fourth step, sorry. We need to do the model training, model testing, and then model validation. So this is something we do always in the loop. And Spark MLlib gives us out of the box those capabilities as well. It gives us algorithms that are already built in, classification, regression, clustering, very known algorithm in the industry. They also give us the ability to construct them and put them together through a concept named pipeline. And pipeline is not invented by Apache Spark. It's a known concept in the data science world. So they're actually leveraging the same concept that exists to make it easier for data scientists to use Apache Spark. And those are the pipelines that helps us construct and put everything together in a nice code so we can work collaboratively within our team. It allows us to tune the machine learning algorithm and also to persist it to disk because later on we want to use it and leverage it further on. But sometimes if we talk to data scientists, they actually need more. And sometimes Spark is just not enough. And this is where we want to branch out. We want to bridge deep learning clusters with Apache Spark. This is something that we see very common in the industry. We see it across different image recognition, video analyzing, also a little bit with NLP world, etc. We want to bridge and leverage the capabilities of the new algorithms that exist today in the industry. When we want to bridge out, we want to find a way to find a tool that can help us translate those data types or different data frames that we work with into the data frames or data formats on the other side. And this is where we're going to use Uber Pathstorm. So Uber developed a tool named Pathstorm. It's an open source data access library that helps us, we can use it on a single node or a distributed training, and basically helps us bridge those different data types and different data formats. So if I'm starting working on my data with PySpark, for example, the Python API for Apache Spark, I can later on, even if I save it in some special format that Spark has, I can later on translate it into the Pathstorm dataset and pull it in using TensorFlow dataset or PyTorch data loader, for example. So it helps me bridge between those two worlds pretty easily. So if I have the Spark data frame, I can use the Pathstorm Spark Inventor and later on pull that information back into a TensorFlow dataset, PyTorch data loader, and leverage their capabilities there. It also gives me the ability to do cache management. I can define if I have specific cache somewhere, I can do that. It allows me to handle MLlib specific types like vectors, sparse, for example, the different type of vectors Spark has in it. And it also helps me migrate from single node to distributed computation if I need to, because I'm later on able to, for example, work with Spark data frame. And if I'm filtering the data out all the way, and later on I only need one small machine, one node to actually do the training, I'm capable of leveraging that as well. So this is a high-level architecture of how the workflow works. We're doing the ETL, entity transfer load, around using Spark and data frame. If there's a cache file that we already define in the system, and we'll see it in a second how we define it, we're leveraging it. If not, we're creating one. And later on, we can pull the information back into TensorFlow, for example, or the PyTorch data loader. So how does it work? Within Pathstorm, there's a library dedicated for Spark, and we can leverage the functionality of make Spark inventor. We do need to set the configuration and give it a specific parquet cache layer, you can see here in the code sample, and then we just give it the data frame and call the functions. We can also use the different Python APIs, like the width definition here, and bring it, actually make the data frame into the data set that we want to work with, and start running some machine learning training on it as well. So let's take a look at the very short demo where we're going to do image processing. So we're going to see basic ETL, handling small files, Pathstorm, and then distributed TensorFlow. Cool. So I'm actually running this locally on a Jupyter notebook, but you can run it in your cloud as well, or any other environment that you're working with. So I'm leveraging a data set named Caltech 256. It's relatively a big data set for image recognition, image classification, and I'm starting my Spark cluster right here. And I have two ways of loading the data, binary or images. I always recommend using the binary file format. It's easier to load, it's more efficient. You can see it loaded into the structure where I have the path, modification time, length, and the actual content. Running forward, there's some operations I'm doing, extracting the label, right? Because we always have to extract the labels. The labels are part of the path. I'm extracting the labels, and I'm starting to run with the feature engineers. For example, I want to gray out my images. So I'm leveraging the different tools that Spark gives me. For example, you can see it. I'm using UDF functionality, and you can see it right there. Applying pandas, also the new pandas UDF that is faster and more efficient. So I'm turning it into a grayscale. You can see it right there. I'm doing it first on an example, like we saw in the beginning. Very short, very small chunk of files first to make sure it works, and later on, I'm doing it on a larger scale. Also, at the end, we talked about a little bit about the file system, the small file system, the small file syndrome. So at the end, I'm making sure to avoid the small files problem by saving it into a parquet, but removing the compressed format, because Apache Spark has a compressed codec out of the box. So we're changing it to uncompressed because we don't need it anymore, because those are images actually. So we don't need to compress it again. It doesn't make sense. And saving it back to this. So this was the first part of working and wrangling the data and extracting those. The second part is actually training my machine learning algorithm, right? So once I have that data, I actually want to start working with my Pathstorm. And I can leverage, you can see here, I'm importing the Pathstorm. I'm also importing Transform Spec. This helps me give specific definitions to the data that I'm working with. And what I want you to see, I want you to see here how I'm setting the cache directory for the data. And later on, how I'm defining the converter train. So remember, at the beginning, I used Spark to do a lot of data manipulation, feature engineering, and all those good things. But later on, I want to leverage an existing machine learning model from the TensorFlow world. So we're going to leverage a mobile net v2. And since it's a neural network, we can always take it, leverage the existing model, and just change the last layer. So we're getting the base layers that already exist. We don't have to train everything from scratch. We can always leverage it and add another layer for the classification in the end. So this is what I'm doing here. I'm taking the mobile net v2 from TensorFlow, and I'm basically getting the model itself, the base model. All this code, by the way, is available for you on a GitHub public repo, so you can look into it. I'm taking the base model, and then I'm training and feeding it into my distributed system later on. So I have the Pathstorm preprocessed because I want to adjust some of the data to fit my machine learning algorithm as well. And then I'm training the distributed model right here. So I have the model, I'm compiling it, defining the different optimizer I want for that specifically. And this is where the Pathstorm thing happens. When I'm converting, make TensorFlow dataset, and here inside, you can already see that I'm leveraging that dataset that I converted from Apache, from Spark data frame into TensorFlow dataset. And I'm training it, running it, only one epoch, some accuracy, some value loss, some more information about the machine learning specifically. But what I want you to take away is exactly the fact that you can leverage both worlds, and you don't have to only be, restricted to Spark MLlib. So I'll wrap up. Now you understand a little bit better the Spark MLlib component and what it gives you. You understand the Spark ML pipelines, how to bridge Spark with TensorFlow and PyTorch. You understand a little bit of how Pathstorm works, and also a nice, cool demo of how those things connect together. All of that exists in my GitHub repo. You can check my Twitter. It's already there on the top. And just to give you a heads up about how the book around this is going to work, there's the book chapter flows distributed into three parts. One is, first of all, working with the data, the feature engineering, the data processing. Second thing is the B part, how we're training with MLlib, how we can train and bridge into PyTorch, how we can train and bridge into TensorFlow. And C is going to be about deployment, triggering, and new machine learning workflow. So thank you so much for your attention. I hope you learned something new today. If you have any questions, I'll be here later on in the Q&A, and also feel free to reach out on Twitter. My DMs are always and forever open. I'm happy to get your feedback, and thank you so much.